About 252 million years ago, the Earth entered one of the most important chapters in its entire history. The world was recovering from the greatest mass extinction ever known. Most plants and animals had disappeared, the land looked almost lifeless in many places, and the oceans had changed in ways that were hard to imagine. Yet, from this difficult beginning, life slowly started to rebuild itself. This was the Triassic Period, a time that lasted for about 50 million years and completely changed the future of life on Earth. During these millions of years, one giant continent covered much of the planet. Vast deserts stretched across the land. Strange reptiles became the dominant animals. The very first dinosaurs appeared, and the earliest true mammals quietly began their journey. The Great Dying happened at the end of the Permian period, a time when life on Earth went through the biggest extinction event that scientists have ever found in the fossil record. It took place about 252 million years ago, at the point where the Permian period ended and the Triassic period began. Before this event, the Earth was full of many different kinds of living things. Oceans contained large reefs, strange fish, shellfish, corals, and many other sea animals. On land, forests stretched across huge areas, while reptiles, amphibians, insects, and many plant species lived in different environments. Over a relatively short period in Earth's long history, much of this life disappeared. Scientists call this event the Permian mass extinction, but it is also widely known as the Great Dying, because of the enormous number of plants and animals that vanished. Studies of rocks and fossils suggest that around 9 out of every 10 marine species disappeared. On land, about 7 out of every 10 species of land vertebrates also became extinct. Many groups that had lived successfully for millions of years were suddenly gone. The Earth that existed after this event looked very different from the one that came before it. To understand why this happened, it helps to look at what the world was like before the extinction. During the late Permian period, almost all of Earth's land was joined together into one giant supercontinent called Pangaea. This enormous landmass stretched across much of the planet. Because it was so large, many places far from the oceans became extremely dry. Rainfall was limited in many inland regions, creating deserts and harsh environments. Coastal areas were often more suitable for life, but even these regions experienced changes in climate over long periods. The oceans also looked different from those of today. Sea levels changed over time, creating shallow seas in some places and exposing land in others. These shallow seas were home to many marine animals. Coral reefs supported large communities of fish and shellfish. Different kinds of brachiopods, trilobites, ammonoids, crinoids, and many other creatures filled the oceans. These animals formed complex ecosystems where countless species depended on one another for food and survival. On land, reptiles were becoming more diverse. Some were large plant eaters, while others hunted smaller animals. Mammal-like reptiles, known as synapsids, were among the most successful land animals of the time. They came in many sizes and shapes. Some had powerful jaws for eating plants, while others were active hunters. Amphibians still lived near rivers, lakes, and wetlands, although many areas were becoming drier than they had been during earlier periods. Plants also covered many parts of the land. Different kinds of seed plants, ferns and conifers formed forests across suitable regions. These forests provided food and shelter for many animals. Insects were abundant as well. They pollinated plants, broke down dead material, and served as food for many larger creatures. For millions of years, life continued to develop across the planet. Then conditions slowly began to change. Scientists studying ancient rocks have found evidence that the environment became increasingly unstable before the extinction reached its worst point. These changes happened over thousands of years rather than all at once. One of the strongest pieces of evidence points to enormous volcanic eruptions in what is now Siberia. These eruptions created a massive volcanic region known today as the Siberian Traps. Instead of lasting for a few days or weeks like many volcanic eruptions today, this period of volcanic activity continued for a very long time. Lava spread across huge areas of land. Layer upon layer of volcanic rock built up over time, covering vast regions. These eruptions released enormous amounts of gases into the atmosphere. Carbon dioxide was one of the main gases produced. Carbon dioxide is a greenhouse gas, meaning it traps heat in the atmosphere. As more of it entered the air, global temperatures began to rise. This warming affected both the land and the oceans. Volcanoes also released sulfur gases. These gases could temporarily cool parts of the planet by reflecting sunlight, but they also contributed to acid rain. Acid rain changed the chemistry of soils, rivers, and lakes. Plants growing in affected regions faced increasing stress. Forests became damaged, making it harder for many animals to find food and shelter. As temperatures continued to rise, many environments became difficult for living things to survive in. Some areas experienced severe drought. Rivers and lakes dried up. Plants that depended on regular rainfall struggled to survive. Animals that relied on these plants soon faced food shortages. Warmer temperatures also affected the oceans. Water naturally holds less oxygen when it becomes warmer. As ocean temperatures increased, oxygen levels began to fall in many places. Marine animals that depended on oxygen-rich water found survival much more difficult. Scientists have discovered evidence that large parts of the oceans became oxygen-poor or even completely without oxygen in some deeper regions. Without enough oxygen, many sea animals simply could not survive. Species that had lived successfully for millions of years suddenly faced conditions they had never experienced before. Another major problem developed as more carbon dioxide entered the oceans. Seawater absorbed much of this gas, causing chemical changes known today as ocean acidification. More acidic water made it harder for many marine organisms to build shells and skeletons made from calcium carbonate. Corals, shellfish, and many tiny organisms struggled to grow and reproduce under these changing conditions. As reefs declined, entire marine ecosystems began to collapse. Reef communities depended on many different species living together. When corals disappeared, countless other organisms lost their homes and feeding grounds. Fish populations declined. Predators lost their prey. Food chains became increasingly unstable. Scientists have also found evidence that dangerous gases, such as hydrogen sulfide, may have become more common in some ocean regions. Certain bacteria produce hydrogen sulfide when oxygen levels become very low. If enough of this gas entered shallow waters or even the atmosphere, it could have harmed many forms of life. Researchers continue to study exactly how important this process was during the extinction. The extinction itself probably did not happen in a single day or even a single year. Evidence suggests that different groups disappeared over thousands of years. Some populations declined gradually, while others vanished more suddenly. Local conditions also varied from one region to another. Some places may have remained suitable for life longer than others, before environmental changes reached them. Marine life suffered the greatest losses. Trilobites, which had lived in Earth's oceans for more than 270 million years, disappeared completely. they never returned. Rugose corals and tabulate corals also became extinct. Many brachiopods vanished. Crinoids declined sharply. Ammonoids nearly disappeared, although a small number survived and later became more diverse during the Triassic. Many types of fish survived, but countless species disappeared. Sharks experienced significant losses as well. The oceans after the extinction contained far fewer species than before. Ecosystems became much simpler because so many different forms of life had vanished. Life on land also changed dramatically. Many mammal-like reptiles became extinct. Large amphibians declined in many regions. Forest ecosystems collapsed in some places. Fossil evidence shows layers containing large amounts of dead plant material, followed by periods where forests were rare or absent. Scientists studying fossil pollen have found evidence that plant communities changed greatly during this time. Some species disappeared completely. Others survived only in limited areas before spreading again as conditions improved. Plants that could tolerate harsh environments often became more common during the earliest Triassic. Insects also experienced major losses. Although insects are generally very successful at surviving difficult conditions, this extinction affected many insect groups. It remains the only known mass extinction in which insects experienced such widespread losses. The disappearance of so many plants had serious effects on land animals. Plant eaters lost their food supply. Meat eaters then lost the plant eaters they depended on. Entire food chains became disrupted. Survival became increasingly difficult for many remaining species. Scientists continue to debate exactly how quickly temperatures increased during this time. Some studies suggest that average global temperatures rose by several degrees over thousands of years. Even gradual warming can cause enormous environmental changes when it continues over long periods. Plants and animals often cannot adapt quickly enough when their habitats change faster than evolution can keep pace. The atmosphere itself may also have contained lower levels of oxygen than before. Some evidence suggests that oxygen concentrations fell significantly during the late Permian and early Triassic. Lower oxygen levels would have made breathing more difficult for large animals and may have limited their activity. Wildfires may also have become more common. Hotter temperatures, dry conditions, and damaged forests created environments where fires could spread more easily. Charcoal preserved in ancient rocks suggests that fires occurred in many regions. These fires further reduced plant cover and added more stress to already struggling ecosystems. As ecosystems broke down, recovery became extremely difficult. Normally, when one species disappears, another may take its place. During the Great Dying, however, environmental conditions remained harsh for a long time. New species could not easily spread because the conditions that caused the extinction continued to affect the planet. The extinction reached nearly every part of the world. Fossils from Asia, Europe, Africa, North America, South America, and Australia all show evidence of major losses. Marine rocks from many different regions record the disappearance of countless sea creatures. Land fossils also show dramatic changes in animal and plant communities. Scientists gather evidence from many different sources to understand what happened. Fossils reveal which species disappeared and which survived. Volcanic rocks help determine when eruptions occurred. Chemical signals preserved in ancient sediments record changes in ocean chemistry, temperature, and oxygen levels. Together, these different forms of evidence create a detailed picture of one of Earth's most difficult periods. Dating methods allow researchers to estimate when events took place with increasing accuracy. Improvements in laboratory techniques have helped scientists narrow the timing of both the volcanic eruptions and the extinction itself. Many studies now suggest that the main extinction occurred during a relatively short period within the much longer history of volcanic activity. Some scientists have explored whether asteroid impacts contributed. Many studies now suggest that the main extinction occurred during a relatively short period within the much longer history of volcanic activity. Some scientists have explored whether asteroid impacts contributed to the extinction. Unlike the extinction that ended the age of the non-avian dinosaurs, there is no widely accepted evidence that a large asteroid was the primary cause of the Great Dying. Most researchers consider the Siberian Trap's eruptions to have played the leading role, although several environmental processes likely work together. Methane may also have added to the warming. Some researchers suggest that warming oceans released methane trapped beneath the seafloor. Methane is an even more powerful greenhouse gas than carbon dioxide over shorter periods. If large amounts entered the atmosphere, temperatures could have risen even further. As the extinction continued, surviving species often existed in very small populations. Small populations face many challenges. They are more vulnerable to disease, environmental changes, and difficulties finding mates. Some species that survived the initial crisis later disappeared because their remaining populations were simply too small. Despite these enormous losses, some forms of life managed to survive. Small reptiles, certain amphibians, a few synapsids, some fish, insects, plants, and many microscopic organisms continued living through the difficult conditions. These survivors became the ancestors of later ecosystems. The beginning of the Triassic Period was not a time of immediate recovery. Instead, it was a world still dealing with the effects of the extinction. Temperatures remained high in many regions. Ocean oxygen levels recovered only slowly. Plant communities took time to spread again. Many environments remained difficult for life. Fossils from the earliest Triassic often show ecosystems with relatively few species. Instead of the rich variety seen before the extinction, only a limited number of organisms dominated many areas. Scientists sometimes describe these early ecosystems as being made up of hardy survivors, that could tolerate difficult conditions. One animal that became especially common in many parts of the world was Lystrosaurus, a sturdy plant-eating synapsid. Fossils of this animal have been found across several continents. Its widespread success suggests that it was well suited to the harsh environments of the early Triassic. Other surviving groups slowly expanded into habitats that had become empty after so many extinctions. With fewer competitors and predators, surviving species had opportunities to spread into new environments. Over many millions of years, evolution produced entirely new groups of animals and plants. The extinction removed many dominant Permian groups that had previously occupied important ecological roles. As these groups disappeared, new opportunities became available. Reptiles gradually became more diverse during the Triassic. Among these reptiles were early members of the Archosaur group, which would eventually include crocodilians, pterosaurs, and dinosaurs. Early dinosaurs did not appear immediately after the extinction. They evolved later during the Triassic, after ecosystems had begun recovering. At first, dinosaurs were relatively small and not especially dominant. They lived alongside many other reptiles that were also evolving and spreading into different environments. The disappearance of many earlier competitors meant that new groups had room to diversify over time. Evolution continued as surviving populations adapted to changing environments. Natural selection favored traits that helped organisms survive the new conditions. Marine ecosystems also slowly recovered. New coral groups eventually formed reefs. Fish populations became more diverse again. Marine reptiles such as ichthyosaurs and nothosaurs later appeared in the oceans, occupying ecological roles that had not existed before the extinction. Recovery took an exceptionally long time compared with many other extinction events. Scientists estimate that complex ecosystems required several million years before they became widely established again. Different regions recovered at different rates, depending on local environmental conditions. The Great Dying therefore marks one of the most important turning points in Earth's history because it separated two very different biological worlds. The Permian world, dominated by many ancient groups, largely disappeared. The Triassic world began with only a small fraction of the earlier diversity, but those surviving organisms gradually gave rise to new forms of life that would shape the rest of the Mesozoic era, including the earliest dinosaurs, the first true mammals, and many other groups that later spread across the planet. The Triassic Period began about 252 million years ago, at a time when Earth was recovering from the greatest mass extinction ever known. Life had been reduced on land and in the oceans after the events that marked the end of the Permian period. Many kinds of plants and animals had disappeared, and the natural world had changed in ways that affected every part of the planet. As the Triassic Period opened, Earth was entering a new stage in its long history. The continents, the oceans, the climate, the rivers, the mountains, and the living things that survived were all part of a world that looked very different from the one that exists today. At the beginning of the Triassic Period, almost all of Earth's land was joined together into one enormous landmass known as Pangaea. This giant continent stretched across a large part of the planet and covered an area much greater than any continent found today. Instead of several separate continents divided by wide oceans, there was one vast body of land connected from one end to the other. Animals could move across long distances without needing to cross large seas. Plants spread across huge areas where the climate allowed them to grow. Rivers carried water through wide valleys, and winds travelled across open land for great distances without meeting an ocean. Pangaea had formed slowly over many millions of years as smaller continents moved toward one another, because of the movement of Earth's outer rocky shell. This movement continued throughout Earth's history, but at the start of the Triassic Period, the continents were still joined together. The edges of the landmass met the surrounding ocean, while the middle of the continent lay far from any coastline. This made conditions in the center very different from those near the sea. The giant ocean surrounding Pangaea was called Pangaea. It covered most of Earth's surface and was much larger than any ocean that exists today. Its waters stretched across enormous distances without interruption. Waves moved across its surface, and ocean currents carried heat from one region to another. Storms formed over its waters and influenced the weather along the coastlines of Pangaea. The size of Pangaea affected the climate of the entire planet, because such a large body of water stored and moved great amounts of heat. Along the eastern side of Pangaea lay another large body of water known as the Tethys Ocean. This ocean extended into the great continent and created long coastlines where marine life could survive and grow. The shallow waters of the Tethys Ocean became home to many sea creatures that had survived the mass extinction. Over time, these waters supported new forms of life as Earth slowly recovered. The shape of Pangaea had a powerful effect on the weather. Much of the land in the center was very far from the cooling influence of the oceans. As a result, temperatures often became extremely high during the daytime. Nights could become much cooler, because dry land loses heat more quickly than water. Rainfall was limited across many inland regions because moist, air from the oceans often lost much of its water before reaching the center of the continent. Large dry areas developed where rivers were few, and lakes were sometimes temporary. Many scientists believe that deserts covered large parts of central Pangaea during the early Triassic period. Strong winds carried fine sand across open ground, building wide fields of sand dunes. Some of these dunes later hardened into rock, leaving evidence that can still be studied today. Layers of sandstone found in different parts of the world show patterns that formed when wind pushed sand across ancient deserts. These rocks help scientists understand the dry conditions that existed during that time. Even though many regions were dry, not every part of Pangaea was a desert. Areas closer to the coasts received more rainfall because they were nearer to the oceans. Rivers flowed from higher ground toward the sea, carrying mud, sand, and small stones. Floodplains formed along river valleys, creating places where plants could grow more successfully. Wetlands developed in some regions, providing homes for animals that depended on fresh water. Mountain ranges also shaped Earth's geography during the beginning of the Triassic period. Some mountains had formed long before the Triassic, as continents slowly collided during the creation of Pangaea. These mountains influenced rainfall by forcing air upward. As air rose, it cooled and released moisture. Areas on one side of the mountains often received more rain than regions lying farther inland. This helped create different environments across the same continent. Many ancient mountain ranges were already wearing down because of wind, rain, rivers, and changes in temperature. Rocks broke apart into smaller pieces that were carried downhill by streams. These materials collected in valleys, river channels, and coastal areas. Over long periods, layers of mud, sand, and gravel built up, later becoming sedimentary rock. These rock layers now provide valuable information about the geography of the early Triassic world. The coastlines of Pangaea stretched for great distances. Some shores were rocky, while others were made of sand or mud. Waves shaped these coastlines every day, moving sediments from one place to another. Tides changed water levels, exposing and covering different parts of the shore. Coastal environments became important places where land and sea met, supporting plants and animals able to live in changing conditions. Large rivers crossed many parts of the continent. Some rivers flowed throughout the year, while others carried water mainly during wet seasons. River systems changed over time as floods reshaped their channels. During periods of heavy rainfall, rivers spread across nearby land, leaving fresh layers of mud behind. During dry periods, water levels dropped, exposing wide riverbeds. Lakes also appeared across different parts of Pangaea. Some were deep and long-lasting, while others existed only for short periods before drying out. Seasonal changes in rainfall often caused water levels to rise and fall. Minerals sometimes collected in drying lakes, forming deposits that later became part of the geological record. Scientists study these deposits to learn about changing climates during the Triassic period. The beginning of the Triassic period was marked by active geological processes beneath Earth's surface. The outer shell of the planet continued to move slowly. Although Pangaea remained joined together, forces beneath the crust were already placing stress on different parts of the continent. Cracks slowly developed in some regions as the land began the long process that would eventually separate into smaller continents many millions of years later. Volcanic activity also played an important part in shaping Earth's geography. Volcanoes released lava, ash, and gases into the atmosphere. Some eruptions built new volcanic landforms, while others covered older landscapes with fresh layers of rock. These volcanic materials later became part of the geological record, helping scientists understand Earth's changing surface during the Triassic Period. Earthquakes occurred as rocks deep underground shifted under pressure. These events sometimes changed the shape of valleys, lifted parts of the land, or created new cracks in the ground. While earthquakes themselves left little direct evidence after millions of years, the rocks affected by these movements provide important clues about ancient geological activity. The climate at the beginning of the Triassic Period was generally warm across much of the planet. There were no large permanent ice sheets covering the poles, as there are during some other periods of Earth's history. Higher temperatures influenced rainfall, evaporation, and wind patterns across both land and sea. Warm conditions affected where plants could survive and where animals could find food and water. Seasonal changes still occurred. Some regions experienced periods of heavier rainfall, followed by long dry seasons. Rivers expanded during wetter times and became much smaller during dry months. Plants had to survive changing water supplies, and animals often depended on seasonal rivers and lakes. The atmosphere also differed from today's atmosphere. Levels of oxygen were lower than those found in the modern world, while carbon dioxide levels were generally higher. These conditions affected both climate and living organisms. Plants continued removing carbon dioxide from the air through photosynthesis, while animals adapted to the conditions that existed during that time. The oceans at the start of the Triassic Period were also recovering from the Great Extinction. Many marine ecosystems had collapsed during the events that ended the Permian period. Coral reefs had been severely damaged, and countless marine species had disappeared. The surviving organisms slowly spread into available habitats as ocean conditions became more stable. Shallow coastal seas became especially important because sunlight reached the sea floor, allowing marine plants and tiny organisms to grow. These organisms formed the base of food chains that supported larger animals. Shell-forming creatures slowly increased in number, and fish populations gradually expanded in many coastal waters. Ocean currents continued moving warm and cooler water across different regions. These currents influenced weather, distributed nutrients, and helped shape marine ecosystems. Changes in ocean circulation affected where different species could survive. Sediments carried by rivers entered the oceans every day. Sand settled near the shore while finer mud travelled farther, before sinking to the bottom. Layer after layer built up over long periods, preserving remains of plants, shells, and other organisms. These sedimentary rocks now help scientists reconstruct the geography of the Triassic world. The land itself supported many different environments, despite the generally dry climate. Some regions contained open plains with scattered vegetation. Others included forests growing where rainfall was more reliable. River valleys supported thicker plant growth because water remained available for longer periods. Low-lying wetlands formed in places where water collected throughout much of the year. Plant life at the beginning of the Triassic Period was still recovering from the earlier extinction. Seed ferns, conifers, cycads, ginkgo relatives, and several other plant groups gradually spread across suitable environments. Their roots helped hold soil together, reducing erosion in many areas. Leaves, branches, and fallen trunks became part of the soil after they decayed, adding nutrients that supported future plant growth. The geography of Earth strongly influenced where these plants could survive. Dry inland deserts supported only plants adapted to limited water supplies, while wetter coastal regions allowed thicker vegetation to develop. Elevation, rainfall, soil type, and seasonal weather all affected plant distribution across Pangaea. This enormous continent contained many different rock types that had formed over Earth's earlier history. Ancient granite, sandstone, limestone, shale, and volcanic rocks all appeared in different regions. Rivers cut through these rocks, exposing layers that recorded events stretching back hundreds of millions of years. Even during the Triassic period, erosion continued uncovering older rocks, while new sediments buried others. Pangaea was the great supercontinent that existed at the beginning of the Triassic period. It was made up of almost all the land on Earth, joined together into one huge landmass. During this time, the planet looked very different from the world we know today. There were no separate continents such as Africa, Asia, Europe, North America, South America, Australia, and Antarctica as they are today. Instead, these lands were connected, forming one enormous continent that stretched across a large part of the planet. This single landmass had a major effect on the climate, the environment, the movement of water and air, and the living things that survived after the largest mass extinction in Earth's history. The Triassic period began after the end of the Permian period. Before the Triassic started, Earth experienced a terrible event that caused the disappearance of most living species in the oceans and on land. Many plants and animals could no longer survive because the conditions on Earth became too harsh. After this great loss of life, the Triassic became a time of recovery. The world was still struggling to return to a stable condition, and Pangaea played a very important part in shaping everything that happened during this period. Scientists believe that Pangaea had been forming for millions of years before the Triassic began. Smaller continents slowly moved toward one another, because the outer layer of Earth is broken into large pieces called tectonic plates. These plates move very slowly over time. As they shifted, land masses collided and joined together. This long process eventually created one giant continent that covered much of Earth's surface. The movement happened so slowly that no living thing could notice it during its lifetime. But over millions of years, the changes became enormous. The name Pangaea comes from ancient Greek words that mean all Earth. This name fits because nearly all the land on the planet was connected into one large body. Around this huge continent was a single great ocean called Pangaea. This ocean covered most of Earth's surface. Along the eastern side of Pangaea lay another large body of water called the Tethys Ocean. These waters influenced weather patterns, temperatures, rainfall, and the movement of marine life during the Triassic. Because Pangaea was so large, many parts of it were very far from the oceans. Today, many places receive rain because moist air moves inland from nearby seas. During the Triassic, the center of Pangaea was often hundreds or even thousands of kilometers away from the nearest coastline. By the time moist air reached these inland areas, much of its water had already fallen as rain near the coasts. As a result, the interior of Pangaea became dry for long periods. Large deserts spread across many inland regions. Sand dunes covered wide areas. Strong winds carried fine dust from one place to another. Rivers were often seasonal. Some flowed only during wetter parts of the year and then became dry as temperatures increased. Lakes sometimes formed after heavy rainfall but later shrank or disappeared as water evaporated. These changing conditions made life difficult for many plants and animals. The Triassic climate was generally warmer than the climate found in many parts of the world today. There were no large permanent ice sheets covering the poles as there are during colder periods of Earth's history. Without these huge masses of ice, global temperatures remained higher. Warm conditions extended across much of Pangaea. Although temperatures still varied from place to place, depending on distance from the sea, elevation, and seasonal changes. Many inland areas experienced very hot summers. During the day, temperatures could rise to uncomfortable levels. At night, temperatures sometimes dropped because dry air does not hold heat as well as moist air. This meant that some places experienced large differences between daytime and nighttime temperatures. Living things had to adapt to these changing conditions if they wanted to survive. Rainfall was uneven across Pangaea. Coastal regions usually received more moisture because they were closer to the oceans. Inland deserts received much less rain. Some regions experienced periods of heavy seasonal rainfall, followed by long dry seasons. This pattern influenced the kinds of plants that could grow and the animals that depended on them. Scientists have found many signs of ancient deserts from the Triassic period. Thick layers of sandstone, preserved sand dunes, and special patterns left by wind all show that dry environments covered large parts of the supercontinent. These rocks provide valuable evidence about the climate that existed millions of years ago. They help scientists understand where deserts formed and how they changed over time. Although many regions were dry, not every part of Pangaea was covered by desert. Rivers flowed across some landscapes, especially near mountain ranges or closer to the coast. Floodplains supported plant life and provided water for many animals. Wetlands also existed in certain areas where enough rainfall collected. These places became important centers for recovering ecosystems after the Great Extinction. Plants during the early Triassic faced many challenges. The mass extinction had destroyed many forests that once covered large areas. Recovery took time. Early plant communities were often made up of hardy species that could survive dry conditions and poor soils. Ferns became especially important because they were among the first plants to spread across damaged landscapes. Scientists often find large numbers of fossil fern spores in rocks from this period, showing how common they became. As conditions slowly improved, other plants spread across Pangaea. Seed ferns, cycads, ginkgo relatives and early conifers became more widespread. These plants had different ways of surviving dry seasons. Some developed thick leaves that reduced water loss. Others produced seeds that could remain protected until conditions became suitable for growth. Their ability to survive changing climates helped rebuild forests and plant communities across many regions. Conifer trees became especially successful in many parts of Pangaea. Their narrow leaves helped reduce the amount of water lost through evaporation. They could grow in soils where other plants struggled. Over time, conifer forests spread across many areas where enough moisture was available. These forests provided food and shelter for many animals that appeared during the Triassic. The distribution of plants across Pangaea depended strongly on climate. Wet coastal regions supported richer vegetation, while dry inland areas had fewer trees and more drought-resistant plants. This uneven pattern influenced where animals lived. Plant-eating animals gathered where food was more plentiful, while meat-eating animals often followed them. The shape of Pangaea also affected wind patterns. Air moved differently across one giant continent than it does across today's separate continents. Warm air rose over heated land, while cooler air moved in from the oceans. Seasonal changes caused shifts in these wind systems. These movements influenced rainfall and helped create periods of wet and dry weather in different regions. Scientists believe that powerful seasonal winds affected many parts of Pangaea. Some regions experienced rainy seasons when moist, ocean air reached the land. Other times of the year became much drier as wind directions changed. These seasonal changes influenced rivers, lakes, plant growth, and animal behavior. Mountain ranges also played an important role in shaping Triassic climates. When air-carrying moisture reached mountains, it rose and cooled. Rain often fell on one side of the mountains while the opposite side remained much drier. This created different environments even within the same part of the supercontinent. Some valleys supported forests while nearby areas remained dry. The coastlines of Pangaea were very long and stretched for thousands of kilometers. Coastal environments included sandy beaches, rocky shores, river mouths, shallow seas, and muddy flats. These places supported many forms of marine life as ocean ecosystems slowly recovered from the mass extinction. Fish, shellfish, marine reptiles, and many smaller organisms found food and shelter in these coastal waters. Life in the oceans also depended on the arrangement of the continents. Ocean currents moved heat and nutrients around the planet. Because almost all land was joined together, these currents followed different paths than they do today. Warm water and cooler water mixed in ways that influenced marine habitats. Areas with nutrient-rich water often supported greater numbers of living organisms. The Tethys Ocean became especially important for marine recovery. Warm, shallow waters allowed many sea creatures to spread into new habitats. Coral-like reef communities slowly returned, although full recovery took millions of years. Many kinds of shellfish, ammonoids, and early marine reptiles became common in these waters. The recovery of marine ecosystems was not immediate. Many ocean species had disappeared during the mass extinction, leaving empty habitats. New species gradually evolved to fill these spaces. Over time, food chains became more stable as plants, small animals, larger predators, and decomposers returned to healthy numbers. On land, insects survived the mass extinction better than many larger animals. They continued pollinating plants, breaking down dead material, and serving as food for other creatures. Beetles, dragonfly relatives, and many other insect groups spread across different environments within Pangaea. Their survival helped support recovering ecosystems. The first part of the Triassic was dominated by reptiles that had survived the extinction. Some looked similar to earlier reptiles, while others developed new body shapes and ways of living. Different groups adapted to deserts, forests, wetlands, and river systems across the supercontinent. As millions of years passed, reptiles became the dominant large land animals. The ancestors of dinosaurs appeared during the Triassic, although they were not yet the dominant animals on land. Early dinosaurs were generally small and lived alongside many other reptile groups. They occupied different habitats, depending on food availability and climate. The conditions created by Pangaea influenced where these early dinosaurs could spread. Because the land was connected, animals could travel across very large distances without crossing wide oceans. This allowed many species to spread into new regions. Fossils of closely related animals have been found on continents that are now separated by vast oceans. These discoveries provide strong evidence that the continents were once joined together as Pangaea. About 252 million years ago, the Earth entered the Triassic Period, a time when the planet was still recovering from the greatest mass extinction that had ever taken place. The natural world looked very different from what people know today. Many kinds of plants and animals had disappeared forever, leaving large empty spaces across land and sea. New forms of life slowly began to spread into these empty places, but they had to survive in an environment that was often extremely difficult. One of the greatest challenges during this time was the climate. Much of the Triassic was known for very hot temperatures, long dry seasons, powerful storms, and weather conditions that could change suddenly. Life had to adjust to these harsh conditions if it was going to survive and continue growing across the world. At the beginning of the Triassic, almost all of the Earth's land was joined together as one giant landmass called Pangaea. Since nearly all continents were connected, there were very few large bodies of water deep inside the land. Most moisture came from the oceans around the edges of the supercontinent. As winds moved across the oceans and reached the land, much of their moisture had already fallen as rain along the coastal regions. By the time these winds reached the center of the continent, they were much drier. This left huge inland areas with very little rainfall. Many places stayed dry for long periods, making it difficult for rivers, lakes, forests, and other sources of fresh water to remain throughout the year. The size of Pangaea also affected how heat spread across the land. During the daytime, sunlight warmed the ground for many hours. Rocks and soil absorbed this heat and became extremely hot. Since there were few large lakes or inland seas to help cool the air, temperatures often continued to rise. Many scientists believe that some inland regions reach temperatures much higher than those found in most places today. During the hottest part of the day, the ground may have become so warm that many animals avoided direct sunlight whenever possible. They searched for shade, rested inside burrows, or became active only during cooler hours. Although the days were often extremely hot, the nights could become much cooler. Dry air does not hold heat as well as moist air. After sunset, much of the heat stored in the ground escaped into the atmosphere. This caused temperatures to fall more quickly than they would in places with higher humidity. Animals living in these areas had to deal with both intense daytime heat and cooler nighttime conditions. Surviving such changes required bodies that could handle different temperatures within a single day. Rain did not fall evenly throughout the Triassic world. Some areas received very little rain for many months. Rivers became smaller or dried up completely. Small lakes disappeared as water slowly evaporated under the hot sun. Plants struggled to stay alive without enough moisture. Many leaves dried out and fell to the ground. Large open spaces with bare soil became common in dry regions. Dust covered the land, and strong winds carried loose sand and soil across great distances. Long periods without rain were sometimes broken by sudden storms. When heavy rain finally arrived, the dry ground often could not absorb water fast enough. Instead of soaking into the soil, water rushed across the surface. Fast-moving floods formed quickly and swept through valleys and river channels. These floods carried rocks, branches, mud, and dead plants over large areas. Even though rain was rare in many places, flooding could still become one of the greatest dangers because of how dry and hard the land had become before the storms arrived. Scientists have found many rock layers from the Triassic that show signs of repeated flooding. Thick layers of mud, sand, and stones were left behind by rivers that suddenly became powerful after heavy rainfall. Some ancient river channels changed direction many times because floodwaters cut new paths across the land. These rock formations help researchers understand that weather during the Triassic often changed between long dry periods and short episodes of very heavy rainfall. The strong sunlight of the Triassic also played an important part in shaping the climate. Without large amounts of cloud cover in many dry regions, sunlight reached the ground almost every day. The land heated quickly each morning and stayed hot throughout the afternoon. Evaporation happened at a rapid rate. Water from rivers, ponds, wetlands, and even damp soil disappeared into the atmosphere. As water became scarce, animals had to travel longer distances to find fresh drinking water. Competition for these limited water sources became an important part of daily survival. Plants faced many difficulties under these conditions. Young plants needed enough moisture to grow, but dry weather often prevented seeds from developing successfully. Only plants with special ways of surviving drought could spread across much of the Triassic landscape. Some developed thick leaves that reduced water loss. Others produced deep roots that reached underground moisture hidden beneath the dry surface. Certain plants completed their life cycle quickly, during short rainy seasons before dry conditions returned once again. The appearance of the landscape changed with the seasons. During wetter periods, grasses, ferns, seed ferns, conifers, and other plants became greener and more widespread. Streams carried fresh water through valleys, and many animals gathered around these places. As dry conditions returned, much of the vegetation became brown or disappeared altogether. Waterholes became smaller each week. Animals had to move constantly in search of food and water as the environment changed around them. Wind was another powerful force throughout much of the Triassic. Open landscapes without thick forests allowed strong winds to travel freely across great distances. These winds lifted dust and sand high into the air. Dust storms may have lasted for hours or even days. Fine particles filled the atmosphere and settled across wide areas. These storms changed the shape of the land by slowly wearing away exposed rocks and moving sand from one place to another. Large sand dunes formed in many dry regions and continued changing shape as winds shifted direction over time. Evidence of these ancient deserts can still be seen today in many parts of the world. Layers of sandstone preserve the patterns left by moving sand dunes. These rocks tell scientists that large desert regions covered significant parts of Pangaea during the Triassic. The size of these deserts shows just how dry much of the climate had become. Not every part of the Triassic world experienced exactly the same weather. Areas closer to the coast generally received more rainfall because they were nearer to the oceans. Moist air from the sea reached these regions more easily. Forests were more common there, and rivers often flowed throughout the year. Farther inland, however, conditions became much drier. The distance from the sea meant that very little moisture reached these central parts of the continent. This created a wide range of environments across the supercontinent, even though the overall climate remained warmer than much of today's world. Seasonal weather patterns also affected many regions. Instead of steady rainfall throughout the year, some places experienced wet seasons, followed by long dry seasons. During the wet months, rivers filled with water, plants grew rapidly, and animals reproduced while food was plentiful. During the dry months, survival became much harder. Many animals migrated towards permanent rivers or lakes, if such places existed. Others reduced their activity to save energy and water until better conditions returned. Some reptiles developed body features that helped them survive the hot climate. Thick skin reduced water loss. Strong legs allowed them to travel long distances between water sources. Many reptiles laid eggs in protected places, where young animals had a better chance of surviving harsh weather. Certain species probably rested during the hottest hours of the day and searched for food during early morning or evening when temperatures were lower. Early dinosaurs appeared during the later part of the Triassic. At first, they were not the largest animals on land. They lived alongside many other reptiles, including crocodile relatives and other ancient groups that later disappeared. These early dinosaurs also faced the challenges of extreme heat, changing seasons, and limited water supplies. Their ability to survive under difficult conditions may have helped them spread into different environments over time. Small mammals that lived during the Triassic were also influenced by the climate. Many were active mainly at night, when temperatures were cooler. Nighttime activity reduced the risk of overheating and helped conserve water. Burrows provided protection from daytime heat as well as from predators. Underground shelters remained cooler than the open ground, making them valuable places to rest during hot afternoons. The oceans experienced changes as well. Warm temperatures affected seawater and influenced marine life. In some shallow seas, water became warmer than many sea creatures could easily tolerate. Changing temperatures affected oxygen levels in the water, making survival more difficult for some species. Marine animals that adapted to these warmer conditions slowly spread through the recovering oceans, while others remained limited to areas where conditions were more suitable. Volcanic activity also influenced Triassic weather. Large volcanic eruptions released gases and tiny particles into the atmosphere. Some gases trapped heat and contributed to warmer global temperatures over long periods. Other volcanic materials temporarily blocked some sunlight until they settled back to the surface. These natural events added even more changes to an already challenging climate. In places near active volcanic regions, ash sometimes covered the ground, affecting plants, rivers, and animals living nearby. After the Great Permian mass extinction, Earth was very different from the world that had existed before. A huge number of living things had disappeared from both the land and the oceans. Many kinds of plants, animals, and tiny living organisms that had once been common were gone forever. Forests had been destroyed in many places. Large areas of land had very little plant life. The oceans had lost many of the creatures that had filled their waters. Food chains had broken apart because many species that depended on one another could no longer survive. The balance of nature had been greatly disturbed, and life had to begin a long process of recovery. The beginning of the Triassic Period marked the start of this slow rebuilding of Earth's ecosystems. Recovery did not happen quickly. It took a very long time before living things spread across the planet, again in large numbers. Many places remained harsh for a long period because the climate was still unstable. Temperatures were often very high, rainfall was uneven, and dry conditions covered large regions. Even with these difficult conditions, life slowly returned. Small groups of surviving plants and animals became the foundation for new ecosystems that slowly expanded over time. Every ecosystem depends on many different kinds of living things working together. Plants produce food through sunlight. Plant-eating animals depend on those plants for food. Meat-eating animals depend on other animals. Tiny organisms break down dead plants and animals, returning nutrients to the soil and water. When many of these living things disappear at once, the entire system becomes weak. During the early Triassic, nature had to rebuild these connections almost from the beginning. Plants played one of the most important roles in this recovery. Without plants, animals could not survive for long. Plants also helped protect the soil from being washed away by rain and wind. Their roots held the ground together, while their leaves provided food and shelter for many small creatures. As plants slowly spread across the land, they created places where other forms of life could return. The first plants to recover were often those that could survive difficult conditions. Many of these plants produced large numbers of spores instead of seeds. Spores are tiny structures that can be carried by the wind over long distances. When they land in suitable places, they can grow into new plants. Ferns were among the plants that became very common during the early stages of recovery. Scientists have found layers of rock from the early Triassic that contain huge amounts of fern spores. This has become known as the fern spike. It shows that ferns quickly spread across many areas after the mass extinction. because they were able to grow in damaged environments where many other plants could not survive. Ferns covered open ground that had once been forests. Their growth helped reduce soil erosion. Their roots held loose soil in place, while their leaves added organic material to the ground after they died. This slowly improved the quality of the soil. Better soil allowed other plants to grow later. In this way, ferns helped prepare the land for the return of more complex plant communities. Other plants also survived the extinction. Some seed-producing plants managed to live through the difficult conditions. These included groups related to conifers, seed ferns, cycads, and ginkgo relatives. Although their numbers had been greatly reduced, they slowly expanded into new areas as conditions became more suitable. Their seeds allowed them to spread over large distances. Some developed thick coverings around their seeds that helped protect young plants during dry periods. Conifer trees became especially important during the Triassic. These trees were well suited to dry climates. Their leaves were often narrow and covered with a protective surface that reduced water loss. Their roots reached deep into the soil in search of moisture. Because of these features, conifers were able to survive in places where broad-leaved plants struggled. Over time, they formed forests across many regions of the supercontinent Pangaea. Cycads also became common in many parts of the world. These plants had thick trunks and large crowns of stiff leaves. They were able to store water and survive periods of drought. Their strong structure allowed them to continue growing even when rainfall was limited. Many animals later depended on cycads for shelter and food. Ginkgo relatives survived as well. These ancient trees had fan-shaped leaves and were able to live in different climates. Although many ancient kinds of ginkgo disappeared over time, some continued to spread during the Triassic. One living species still exists today, showing how successful this ancient group has been over an extremely long period. As plants spread, insects also began to recover. Insects had suffered greatly during the extinction, but many groups survived. Beetles, dragonflies, flies, and other insects slowly increased in number. They fed on plants, dead material, and other insects. Their activities helped recycle nutrients and supported the rebuilding of ecosystems. Some insects bored into wood, helping dead trees break down more quickly. Others fed on leaves or seeds. Many insects became food for reptiles, amphibians, and early mammals. Their return provided an important source of nutrition for many animals that were trying to survive in recovering environments. Tiny organisms living in the soil also played an important part in recovery. Bacteria and fungi broke down dead plants and animals. As they did this, nutrients were released back into the soil. Plants then absorbed these nutrients through their roots. This natural cycle helped improve the fertility of the land. Healthy soil allowed larger plants to grow, which supported larger animal populations. Freshwater environments also slowly recovered. Rivers, lakes, and wetlands had been badly affected by the extinction. Fish populations had fallen sharply, and many freshwater animals had disappeared. As water quality improved and plants returned to riverbanks, freshwater ecosystems slowly became healthier. Fish began to increase in number, providing food for reptiles and amphibians. Amphibians were among the first large land animals to recover. Many early amphibians lived near rivers, lakes, and marshes because they needed water for reproduction. Their young usually developed in water before becoming adults. These animals fed on fish, insects, and other small creatures. Some became very large during the Triassic. Temnospondyle amphibians were especially successful. Some had broad heads, powerful jaws, and long bodies. Many spent most of their lives in water, waiting for prey to come close before attacking. Their ability to live in freshwater habitats allowed them to survive while many land environments remained difficult. Reptiles gradually became more important as recovery continued. Reptiles had several advantages that allowed them to live in dry environments. Their skin reduced water loss, and many laid eggs with protective shells that did not need to be placed in water. These features allowed reptiles to spread into regions where amphibians could not easily survive. Many different reptile groups appeared during the Triassic. Some remained small and fed on insects. Others became plant eaters or meat eaters. Their bodies showed many different shapes because they were adapting to different ways of life. Some had long legs for running, while others had shorter limbs for walking through thick vegetation or along riverbanks. Archosaurs became one of the most successful reptile groups during this time. This group later gave rise to dinosaurs, crocodilians, and flying reptiles. Early archosaurs explored many different habitats. Some hunted small animals, while others fed on plants. Their success came from their ability to adapt to changing environments. Crocodile relatives appeared during the Triassic as well. Some lived mostly in water, while others spent much of their time on land. Their powerful jaws allowed them to catch fish, amphibians, and small reptiles. Over time, different crocodile relatives developed different hunting methods depending on where they lived. Early dinosaurs were only a small part of Triassic ecosystems at first. They did not immediately become the dominant animals on land. Instead, they lived alongside many other reptiles. Most early dinosaurs were relatively small. Some walked on 2 legs, while others moved on 4. They hunted insects and small animals or fed on plants, depending on the species. One reason dinosaurs eventually became successful was their efficient movement. Many early dinosaurs had upright legs positioned directly beneath their bodies. This body structure helped them move with greater endurance. It also allowed them to travel longer distances in search of food and water across the dry landscapes of the Triassic. Small mammal relatives also survived and continued evolving during this time. These animals descended from earlier synapsids, which had once dominated land ecosystems before the mass extinction. Most Triassic mammal relatives were small, often active during the night, and fed on insects, seeds, and other small food sources. Their small size helped them hide from predators and survive in changing environments. They likely lived in burrows, fallen logs, and dense vegetation. Living underground protected them from extreme daytime heat and many predators. Their fur helped maintain body temperature, and their sharp teeth allowed them to eat many different kinds of food. This flexibility in diet increased their chances of survival. Instead of depending on only one food source, they could switch to different foods when conditions changed. This ability became very important during a time when ecosystems were still rebuilding and food supplies were often limited. The oceans also experienced a long recovery. Many marine animals had disappeared during the extinction. Coral reefs were almost completely destroyed in many places. Shellfish, fish, and countless tiny ocean organisms had suffered enormous losses. Recovery beneath the sea took many millions of years as new marine communities slowly formed around surviving species. The early Triassic oceans were much quieter than they had been before the Great Extinction. Many kinds of sea animals that had once filled the shallow seas no longer existed. Empty spaces remained in many marine environments because there were very few living creatures left in to occupy them. The rebuilding of ocean life happened slowly as the surviving animals spread into these open areas and began producing new generations. Over many years, the number of marine species slowly increased, and the relationships between different forms of life gradually became stronger. tiny living organisms were among the first to help rebuild the oceans. Although they were too small to be seen without special equipment, they played an important role in keeping marine ecosystems alive. Many floated near the surface of the sea, where sunlight reached the water. Others lived on the sea floor or inside the mud. These tiny organisms became food for slightly larger animals, beginning new food chains that slowly became more complex. Simple algae also became important during this period. Algae used sunlight to produce food, just as land plants did. They released oxygen into the water and formed the base of many marine food chains. Small animals fed on algae, while larger animals fed on those smaller creatures. As algae spread through the oceans, they supported the return of many different forms of marine life. Many shell-producing animals slowly returned. Clams, snails, and other mollusks began increasing in number again. Some lived partly buried in the sea floor, where they filtered tiny food particles from the water. Others crawled across the bottom, searching for food. Their growing populations provided food for fish and marine reptiles that appeared later in the Triassic. Ammonoids were among the most successful marine animals during the recovery. These relatives of modern squids and octopuses lived inside coiled shells. Although many ammonoid species had disappeared during the mass extinction, a small number survived. These survivors multiplied rapidly and spread through many parts of the world's oceans. Over time, many new ammonoid species appeared, each with shells of different shapes and patterns. Their fossils are found in rocks from many parts of the world because they became so widespread. The success of ammonoids shows how quickly some groups of animals could recover when they found suitable conditions. They reproduced in large numbers and spread into many different marine environments. Their shells protected their soft bodies from some predators, while their ability to swim allowed them to search for food over wide areas. Bivalves also became increasingly common. These animals had two shells joined together by a hinge. Many remained buried beneath the sand or mud, while others attached themselves to rocks or hard surfaces. They filtered tiny food particles from seawater, helping keep the water cleaner. Their feeding activities also moved nutrients through the ecosystem. Sea lilies, which belong to the echinoderm group, slowly returned in some marine habitats. These animals attached themselves to the seafloor using long stems. Their feathery arms captured tiny food particles floating in the water. Although they had suffered greatly during the extinction, surviving species slowly expanded into areas where conditions improved. Sea urchins also recovered in many places. These animals fed on algae and other material growing on rocks and the sea floor. As they grazed, they helped shape marine communities by controlling the growth of certain organisms. Their activities allowed many other species to share the same habitats. Fish populations slowly increased as marine ecosystems became healthier. Different groups of fish filled different roles within the food chains. Some fed on tiny floating organisms. Others hunted shellfish, worms, or smaller fish. As fish became more numerous, they provided food for larger predators, including marine reptiles. Ray-finned fish became one of the most successful groups during the Triassic. Their bodies allowed efficient movement through the water, helping them escape predators and search for food. Over time, they evolved into many different forms that occupied rivers, lakes, shallow seas, and deeper marine environments. Sharks also survived the Great Extinction, although many ancient species disappeared forever. The surviving sharks slowly recovered as fish populations increased. They hunted weaker animals and helped maintain healthy fish populations by removing sick or injured individuals. Different shark species developed different feeding habits depending on where they lived. Marine reptiles became one of the most remarkable parts of Triassic ocean recovery. These reptiles had ancestors that once lived on land, but gradually adapted to life in the sea. Their bodies changed over many generations, allowing them to swim more effectively and hunt marine animals. Ichthyosaurs were among the earliest marine reptiles to become widespread. They had long bodies, strong tails, and limbs that had changed into flippers. Many hunted fish and ammonoids. Their large eyes suggest that some species may have hunted in deeper or darker water where light was limited. Fossils show that ichthyosaurs gave birth to live young in the water instead of laying eggs on land. This allowed them to spend their entire lives in the sea. Nothosaurs lived mainly in shallow coastal waters. They had long necks, sharp teeth, and strong swimming abilities. They often hunted fish close to shore and rested on land or rocky coastlines when necessary. Their bodies show that they were adapted for both swimming and limited movement on land. Placoodonts were another unusual group of marine reptiles. Many had broad, flat teeth that crushed shellfish. Their powerful jaws allowed them to break open hard shells and eat the soft animals inside. Some placoodonts developed heavy protective plates covering parts of their bodies, giving them extra protection from predators. These marine reptiles occupied different parts of the ocean ecosystem. Because they hunted different kinds of prey and lived in different environments, many species were able to exist together without depending on exactly the same food sources. This helped increase the overall stability of marine ecosystems. Coral reefs did not recover quickly. The reef-building corals that had existed before the extinction had suffered enormous losses. For a long time, many shallow tropical seas lacked the rich reef systems that had once supported countless marine species. Other organisms temporarily filled some of these empty spaces until reef-building corals slowly became more common again later in the Triassic. Sponges became especially important during parts of this recovery. Some sponge communities formed structures that provided shelter for fish, shellfish, and many smaller animals. These simple organisms filtered large amounts of water every day, removing tiny food particles and helping improve water quality. As marine life expanded, food chains became longer and more complex. Tiny organisms supported small animals. Small animals supported fish. Fish supported larger fish, sharks, and marine reptiles. Dead organisms sank to the sea floor, where bacteria and other decomposers broke them down. Nutrients released during decomposition became available for new generations of marine plants and microorganisms. The movement of nutrients became an important part of rebuilding ocean ecosystems. Every living thing depended on this continuous cycle. Without decomposers returning nutrients to the environment, plants and algae would eventually run out of the materials needed for growth. The recovery of these natural cycles allowed marine life to become more productive over time. On land, forests continued expanding into new areas as conditions slowly improved. Young trees replaced open ground that had once been almost empty after the extinction. As forests grew thicker, they created cooler and more sheltered environments beneath their branches. Fallen leaves built layers of organic material on the forest floor. This material slowly broke down into rich soil that supported many smaller plants. Different kinds of plants occupied different environments. Some grew best along rivers where water remained available throughout much of the year. Others became established in drier uplands where rainfall was less reliable. This variety of plant life created many different habitats for animals. Small reptiles hunted insects among fallen leaves. Larger plant-eating reptiles fed on leaves, stems, and seeds. Meat-eating reptiles followed these plant-eaters, creating more complete food chains. Each new species that became established added another connection. to the growing ecosystem. Burrowing animals also became increasingly important. By digging into the soil, they mixed different layers of earth together. Their tunnels allowed air and water to move more easily beneath the ground. Plant roots often benefited from these improved soil conditions. Burrows also provided shelter for many other animals during periods of extreme heat or drought. Some animals became active mainly during daylight, while others searched for food after sunset. This pattern reduced competition for food and shelter. Night activity also helped smaller animals avoid the hottest part of the day, which remained especially important during the warm climate of the Triassic. The rebuilding of ecosystems happened at different speeds in different parts of the world. Some regions recovered more quickly because they received more rainfall or experienced fewer environmental disturbances. Other areas remained dry and difficult for much longer. Local conditions shaped which plants and animals became successful in each region. As generations passed, living things slowly adapted to their environments. Individuals with useful features were more likely to survive, reproduce, and pass those features to their young. Over many generations, these small changes produced new species that were better suited to the conditions of the Triassic world. The recovery of Earth's ecosystems was therefore not simply the return of the old world that had existed before the extinction. New communities gradually formed as surviving plants and animals spread into empty habitats, adapted to changing environments, and gave rise to entirely new branches of life that would continue developing throughout the rest of the Triassic period. The rise of the earliest reptiles was one of the most important parts of the history of life on Earth. These animals appeared during a time when the land was already home to many kinds of living things. But the world was still changing in many ways. Long before dinosaurs, birds, and mammals became important, the first reptiles slowly spread across forests, riverbanks, dry plains, and many other places. Their success came from special features that allowed them to live on land more easily than many earlier animals. Over a very long period, they became some of the most successful land animals on Earth, and gave rise to many groups that appeared later. Before reptiles appeared, life had already spent millions of years changing and becoming more complex. The earliest living things stayed in the oceans because water protected them from drying out and provided a place where they could reproduce. Small plants and animals slowly evolved into many different forms. Fish became one of the most successful groups in the seas and freshwater environments. Some fish later developed stronger fins and lungs that allowed them to survive in shallow water, where oxygen levels often changed. These changes became very important because they helped prepare some animals for life on land. The first animals to spend time on land were early amphibians. These animals were able to walk on land, but they still depended heavily on water. Their skin had to remain moist because it dried out easily. They also returned to ponds, lakes, rivers, and wetlands to lay their eggs. Their eggs did not have enough protection to survive in dry places. Because of this, amphibians could not move very far from water for very long. Even though they were among the first successful land animals, their lives were still closely connected to wet environments. As time passed, the land itself became richer in life. Large forests spread across many parts of the world. Huge trees, giant ferns, seed ferns, horsetails, and club mosses covered wide areas. Thick plant growth created homes for insects, spiders, and many other small animals. Some insects became very large because the atmosphere contained high amounts of oxygen. Rivers crossed the land, and swamps covered many low areas. These environments supported many kinds of life and provided food for growing animal populations. Living on land brought many new problems. Animals had to support their own body weight because they no longer floated in water. They had to protect themselves from drying out. They also needed better ways to breathe air, move across rough ground, find food, escape predators, and reproduce without depending on water. Different groups of animals solved these problems in different ways. Among all these changes, reptiles developed one of the most successful solutions. One of the biggest reasons for the success of reptiles was the development of the amniotic egg. This type of egg was very different from the eggs laid by amphibians. Instead of needing to remain in water, it contained everything the growing young animal needed while inside the shell. Special membranes surrounded the developing embryo. These membranes held water, supplied food, stored waste, and allowed gases to pass through. The shell protected the egg while still allowing oxygen to enter. Because of this design, reptiles could lay their eggs on land without returning to ponds or rivers. This single change opened many new opportunities. Reptiles could spread into places that were too dry for amphibians. They no longer needed to remain close to wetlands during the breeding season. They could move across forests, open land, rocky places, and dry regions while still producing young successfully. This freedom allowed reptiles to occupy many different environments. Another important feature was their skin. Reptiles developed dry skin covered with scales. These scales helped reduce water loss. Unlike amphibian skin, reptile skin did not need to stay wet all the time. This allowed reptiles to spend much longer periods in dry places without becoming dehydrated. Their skin also provided protection against injury and some harmful conditions in the environment. The bodies of reptiles also became stronger for life on land. Their limbs supported their weight more effectively than many earlier animals. Stronger bones and muscles allowed them to move over rough ground, climb obstacles, dig into soil, and chase prey. Different reptile groups later developed different body shapes depending on how they lived, but the earliest reptiles already showed important improvements that helped them survive. Their breathing system also worked well on land. Their lungs became more effective than those of many earlier amphibians. Strong muscles helped move air into and out of the lungs. This allowed reptiles to remain active in different environments and helped support larger body sizes as evolution continued. Reptiles also improved the way their bodies controlled water. Their kidneys became better at conserving water, allowing them to survive in drier environments. They produced waste in forms that reduced water loss. These changes may seem small, but together they made life away from water much easier. The earliest reptiles appeared during the Carboniferous period, which began more than 350 million years ago and ended about 299 million years ago. During this time, large forests covered much of the land. Warm temperatures and widespread wetlands created ideal conditions for many forms of life. Although amphibians were still common, reptiles slowly began establishing themselves in these environments. One of the earliest known reptiles is often identified as Hylonomus. This small animal lived about 315 million years ago. It was not large or frightening. It was only about the length of a human hand. It probably fed on insects and other small animals. Fossils of Hylonomus have been found inside the remains of ancient tree stumps, suggesting that it may have used hollow logs for protection from predators and harsh weather. Hylonomus had many features that clearly separated it from amphibians. Its body was better suited for dry land. It had stronger limbs, reptile skin, and the ability to lay amniotic eggs. Although it looked simple compared with later reptiles, it represented an important step in the history of life. Another early reptile was Paleothyrus. This animal lived during a similar period and also showed many reptile features. It was small, fast, and probably hunted insects and other tiny creatures living among fallen leaves and forest plants. Animals like Paleothyrus filled important roles in the food chain by feeding on smaller animals while avoiding larger predators. The world during this period was filled with many dangers. Large amphibians hunted in wetlands. Giant insects moved through forests. Early relatives of reptiles searched for food across the forest floor. Survival depended on staying alert, finding food, avoiding predators, and producing healthy young. As reptiles became more successful, they gradually evolved into different groups. Some remained small insect eaters. Others became larger hunters. Some developed stronger teeth for eating hard food, while others became plant eaters. Over millions of years, this growing variety allowed reptiles to occupy many different ecological roles. Climate changes also helped shape reptile evolution. Toward the end of the Carboniferous period, many areas became drier. Wet forests began shrinking in some regions. Swamps disappeared from certain places, and open landscapes became more common. These changes created problems for amphibians because they depended on water for reproduction. Reptiles, with their protected eggs and water-saving bodies, handled these changing conditions much better. As dry environments spread, reptiles expanded into places where amphibians struggled to survive. This allowed reptile populations to increase. Different groups became separated by mountains, rivers, deserts, and changing climates. Isolation encouraged new species to evolve over time. The arrangement of Earth's continents also influenced reptile evolution. During the late Carboniferous and early Permian periods, most land was gradually joining together into the giant supercontinent called Pangaea. Large connected land areas allowed animals to spread over enormous distances. Populations moved into new environments where they faced different conditions. These differences encouraged further evolution. The Permian period began about 299 million years ago and lasted until about 252 million years ago. During this time, reptiles became even more successful. Many new forms appeared. Some remained small while others reached much larger sizes. Their diets became more varied. Their bodies became more specialized for different ways of life. Among the early reptile groups were the captorhinids. These reptiles usually had broad heads and strong jaws. Some species ate insects while others fed on plants. Their teeth became well suited for processing different foods. This flexibility helped them survive in changing environments. Another important group included the Protorothririds. These reptiles remained fairly small and probably hunted insects and other tiny animals. They showed many features seen in early reptiles and helped scientists understand how later groups evolved. As reptile evolution continued, one of the biggest developments involved the skull. Different reptile groups developed different openings behind the eye sockets. These openings allowed stronger jaw muscles to attach, improving the force of the bite. Scientists used these skull features to divide early reptiles into major evolutionary groups. Some reptiles had no openings behind the eyes. These are often called anapsids. Others developed one opening, becoming known as synapsids. Another group developed two openings and became known as diapsids. These differences eventually led to many important branches of animal evolution. The synapsids became especially important because they eventually gave rise to mammals many millions of years later. Although early synapsids looked reptile-like, they followed their own evolutionary path. They developed many new features over time that later appeared in true mammals. One famous early synapsid was Dimetrodon. It lived during the Permian period and became one of the top predators in many environments. It had powerful jaws filled with sharp teeth. A large sail rose from its back, supported by long bones extending upward from the spine. Scientists continue studying exactly how this sail functioned, but it may have helped regulate body temperature or played a role in display. Despite often appearing in books beside dinosaurs, Dimetrodon lived millions of years before the first dinosaurs evolved. It belonged to the synapside group rather than the dinosaur lineage. Many other synapsids also appeared during the Permian. Some became plant-eaters with heavy bodies and strong jaws. Others remained meat-eaters. This variety showed how quickly different evolutionary paths could develop once reptiles established themselves on land. The diapsids followed another important path. This group eventually produced crocodiles, lizards, snakes, turtles, through later evolutionary events, pterosaurs and dinosaurs. Birds also evolved much later from certain dinosaur groups. The earliest diapsids were small animals, but they became the ancestors of many later reptiles. Early reptiles lived in many habitats. Dense forests offered shelter and food. Dry plains supported different plants and insects. Riverbanks attracted animals searching for water. Rocky hills provided hiding places from predators. Each habitat presented unique challenges, encouraging different adaptations. Food sources also varied greatly. Insects formed an important part of many reptile diets. Beetles, cockroach relatives, dragonflies, and many other insects were abundant. Small reptiles hunted these creatures using quick movements and sharp teeth. Larger reptiles hunted amphibians, fish, and smaller reptiles. Plant-eating reptiles fed on leaves, stems, seeds, and other plant material. Predators constantly shaped reptile evolution. Animals that moved quickly escaped danger more often. Those with stronger jaws caught prey more successfully. Better eyesight, improved hearing, stronger muscles, and protective skin all increased survival chances. Every generation passed useful traits to its young if those traits helped individuals survive long enough to reproduce. Reproduction remained one of the greatest strengths of reptiles. By laying protected eggs on land, they avoided many dangers found in water. Fish and amphibian eggs often became food for predators living in ponds and rivers. Reptile eggs hidden under soil, leaves, or sand sometimes had better protection. Parents of many early reptiles probably provided little or no care after laying eggs, but the egg itself gave developing young a much safer start. Young reptiles hatched looking much like smaller versions of adults. Unlike amphibians, they did not need to pass through a tadpole stage in water. This direct development allowed them to begin life immediately on land. It reduced dependence on aquatic habitats and supported further expansion into dry regions. The plant world also continued changing during this time. Seed plants became increasingly important. Their seeds survived dry conditions much better than spores. As plants adapted to changing climates, reptiles feeding on vegetation also changed. Plant eaters developed stronger jaws, different teeth, and larger digestive systems, capable of handling tougher plant material. The relationship between plants and reptiles influenced ecosystems across the land. Plant-eating reptiles affected which plants became common. Meat-eating reptiles controlled populations of smaller animals. Insects fed on plants while becoming food for reptiles. These interactions helped create stable food webs that continued evolving over millions of years. The atmosphere and climate continued changing throughout the Permian period. Many regions became hotter and drier as the supercontinent expanded. Inland areas often received less rainfall than coastal regions. Seasonal weather became stronger in many places. Animals capable of conserving water gained important advantages. Reptiles continued spreading across these changing environments because of their body design. They could survive where water was less available. Their eggs remained protected from drying out. Their skin reduced water loss. Their kidneys conserved moisture. Together, these features allowed reptiles to occupy large parts of the land. Fossils show that reptiles became increasingly diverse during the Permian period. Scientists have discovered skeletons, footprints, eggs, and even fossilized skin impressions that reveal details about their lives. Careful study of these remains helps researchers understand movement, growth, feeding habits, and evolutionary relationships. Many fossil discoveries come from rocks that were once river valleys, floodplains, deserts, forests, and lakes. Each location preserves different kinds of evidence. Some fossils show complete skeletons. Others preserve only skulls, teeth, footprints, or isolated bones. Even small discoveries can provide important information. Scientists examine the shapes of bones very carefully. The length of limbs shows how animals moved. Tooth shape reveals diet. Skull openings help identify evolutionary relationships. Bone growth patterns show how quickly animals matured. Modern technology allows researchers to study fossils without damaging them. Computed scanning methods allow scientists to see inside fossils hidden within rock. Digital models help reconstruct missing parts. Careful measurements reveal tiny differences between species. These methods continue improving our understanding of early reptiles every year. The history of early reptiles was also affected by volcanic activity, shifting continents, changing sea levels, and changing climates. These environmental changes sometimes created new habitats while destroying others. Animal populations constantly adapted, moved, or disappeared as conditions changed. Competition for food also influenced evolution. When many animals depended on the same food source, individuals with useful adaptations often survived better. Slight improvements in speed, jaw strength, eyesight, or body shape could increase survival. Over many generations, these small changes accumulated and produced new species. Disease and parasites probably affected early reptiles just as they affect animals today. Fossil evidence sometimes shows healed injuries, damaged bones, infections, or bite marks. These discoveries remind scientists that ancient animals experienced many of the same biological challenges seen in living animals. Some reptiles probably lived alone, while others may have gathered during breeding seasons or where food was plentiful. Direct evidence for behavior is rare, but fossil trackways sometimes suggest groups of animals moving together across ancient landscapes. Daily activity likely differed among species. Some reptiles may have hunted during daylight, using eyesight to locate prey. Others may have been more active during cooler parts of the day or at night. Environmental conditions often influenced activity patterns. Growth from hatchling to adult required surviving many dangers. Young reptiles faced predators from insects, amphibians, larger reptiles, and other meat-eaters. Only a small number probably survived long enough to reproduce. This high level of natural selection helped shape stronger future generations. As millions of years passed, reptiles continued changing into increasingly specialized forms. Some developed longer necks, others became heavily built. Different limb structures appeared for climbing, digging, swimming, or fast movement across open ground. Jaw designs became more varied as diets expanded. These evolutionary changes prepared reptiles for future success after the greatest mass extinction in Earth's history at the end of the Permian period, about 252 million years ago. That disaster eliminated many kinds of living things across both land and sea. Numerous reptile groups disappeared, but some survived. The surviving reptiles later diversified during the Triassic Period, eventually leading to the appearance of dinosaurs, crocodile relatives, flying reptiles, marine reptiles, and many other groups that shaped life on Earth for millions of years. The earliest reptiles themselves were not huge animals that ruled the world overnight. Their success came slowly through countless generations. Small improvements accumulated over extremely long periods. Their ability to reproduce on land, conserve water, move efficiently, breathe effectively, and adapt to changing environments allowed them to spread into habitats that earlier animals could not fully occupy. These features laid the foundation for one of the longest and most successful chapters in the history of animals living on land. The first dinosaurs appeared during the Middle Triassic Period, long after life on Earth had begun to recover from the greatest mass extinction in the planet's history. The world they entered was very different from the one people know today. Large areas of land were joined together into one giant landmass called Pangaea. Most regions were dry, hot, and received only seasonal rainfall. Forests covered some places, while many other areas were open, dusty, and filled with rivers that changed their paths over time. Plants and animals were slowly spreading into empty habitats after many older forms of life had disappeared. This changing environment created new chances for many kinds of living things. Among these were a small group of reptiles that would later become known as the first dinosaurs. The earliest dinosaurs were not huge animals. They did not rule the land when they first appeared. They were small, light, and active creatures that lived beside many other reptiles. At first, they made up only a tiny part of the animal life on Earth. Many larger reptiles were already successful hunters or plant eaters. Crocodile relatives, armored reptiles, meat-eating reptiles, and many other groups were common across the land. The first dinosaurs had to live in a world where they faced competition for food, water, and shelter. Their early success came slowly over millions of years, rather than happening all at once. Scientists believe that the ancestors of dinosaurs belonged to a larger group of reptiles called archosaurs. This group also included the ancestors of crocodiles and several other reptiles that lived during the Triassic Period. Archosaurs had already developed many features that helped them survive on land. They had stronger legs than many earlier reptiles, better breathing systems, and body structures that allowed them to move more efficiently. Over time, one branch of these reptiles began to develop features that separated them from the others. These animals became the first true dinosaurs. One important feature of the earliest dinosaurs was the way their legs were positioned. Unlike many older reptiles whose legs spread outward from the sides of the body, dinosaur legs stood directly beneath the body. This gave them a more upright posture and allowed them to walk, run, and turn more easily. Their movement required less energy during long periods of activity. This body design became one of the most important characteristics shared by nearly all dinosaurs that appeared later. The first dinosaurs were generally small animals. Many were no taller than a person, and some were much smaller. Several early species weighed only as much as a medium-sized dog or goat. Their small size allowed them to move quickly through forests, across riverbanks, and over open ground. They could hide among plants, fallen logs, and rocks when larger predators came near. Their light bodies also helped them travel long distances in search of food and water. One of the earliest known dinosaurs is Eoraptor, whose name means dawn thief. It lived about 231 million years ago in what is now Argentina. Fossils of this animal show that it was a small dinosaur measuring about 1 meter in length. It weighed only around 10 kilograms. Its long legs suggest that it could run quickly. It had sharp teeth that may have allowed it to eat small animals, insects, and perhaps some plants as well. Scientists continue to study its fossils because they provide important clues about how the earliest dinosaurs lived. Another early dinosaur was Herrerasaurus. It also lived in what is now Argentina during the late Triassic period. This animal was larger than many other early dinosaurs, reaching several meters in length. It had powerful jaws filled with sharp teeth designed for catching prey. Strong legs helped it chase smaller animals across open ground. Although it looked more advanced than some earlier dinosaurs, it still showed several features that reveal how dinosaurs were only beginning their long history. Another important early dinosaur was Eodromeus, whose name means dawn runner. Fossils discovered in South America show that it was a fast-moving meat-eater. It had a slender body, long tail and long legs that helped it stay balanced while running. Its hands were able to grasp prey, making it an effective hunter of small animals. This dinosaur lived during the same general period as several other early dinosaurs, showing that different dinosaur species were already developing in the same environments. Scientists have also discovered fossils of Saturnalia in Brazil. This small dinosaur lived during the late Triassic period and is believed to have been one of the earliest relatives of the giant, long-necked dinosaurs that appeared much later. Even though its distant descendants became some of the largest animals ever to walk on land, Saturnalia itself was small and lightly built. It probably ate both plants and small animals, depending on what food was available. This flexible diet may have helped it survive during changing seasons. The climate during the Triassic period placed many challenges before the first dinosaurs. Much of the land experienced long dry seasons, followed by periods of heavy rain. Rivers sometimes dried up before flowing again after seasonal storms. Lakes expanded and shrank over time. Food supplies often changed from one season to another. Animals that could travel quickly, find different food sources, and adapt to changing conditions had a better chance of surviving. The early dinosaurs possessed many of these abilities. The plants that surrounded the first dinosaurs were different from the flowering plants seen today. There were no grasses covering wide plains. Instead, the land supported forests of conifers, cycads, seed ferns, horsetails, and many kinds of ferns. Mosses covered damp areas near streams and rivers. These plants provided food for plant-eating animals and shelter for insects, small reptiles, and other creatures. Early dinosaurs lived among these ancient plants as they searched for food and avoided danger. Insects formed an important part of many ecosystems during this time. Beetles, dragonflies, cockroach relatives, and many other insects lived among the forests and wetlands. Small dinosaurs probably hunted these insects whenever they had the chance. Insects provided a rich source of food that required little effort to catch compared with larger animals. Small reptiles, amphibians, and young animals also became food for early meat-eating dinosaurs. The first dinosaurs shared their world with many other reptiles that were often larger and more numerous. Some reptiles had thick armor covering their bodies. Others had long jaws filled with sharp teeth. Giant amphibians still lived in rivers and lakes. Early crocodile relatives hunted along river banks. Flying reptiles known as pterosaurs had already begun to appear in the skies. The first dinosaurs lived as only one part of this rich collection of animals rather than being the dominant group. Fossils show that early dinosaurs were spread across several parts of Pangaea. Since all the continents were connected, animals could move across large areas without crossing oceans. Populations slowly spread into new regions as they searched for food and suitable habitats. Fossils found in South America, Africa, North America, Europe, and India show that dinosaurs became established across much of the supercontinent during the Triassic Period. Their wide distribution helped different groups develop in different environments. The bones of the first dinosaurs reveal much about how they lived. Their leg bones show strong muscles that supported active movement. Their hips display the special arrangement that identifies true dinosaurs. Their arms varied depending on the type of food they ate. Some had hands better suited for grasping prey, while others gradually developed features useful for feeding on plants. Their teeth also differed according to diet. Sharp, curved teeth helped catch animals, while leaf-shaped teeth became useful for eating vegetation. The tails of early dinosaurs played an important role in balance. As these animals ran, turned, or changed direction, their tails helped keep the body steady. Long tails also supported the muscles needed for movement. This feature remained important in many dinosaur groups for millions of years. Although tail shapes changed among different species, balance continued to be one of their main functions. Scientists study fossil footprints as well as bones to understand how the first dinosaurs behaved. Some trackways show animals moving alone, while others suggest that several individuals traveled through the same area. Footprints preserved in ancient mud reveal walking speed, direction of travel, and even changes in behavior during different parts of the day. These fossil tracks add valuable information that bones alone cannot provide. Growth patterns preserved inside fossil bones show that many early dinosaurs grew steadily during their early years. By examining thin slices of fossil bone under powerful microscopes, scientists can identify growth rings and blood vessel patterns. These features help estimate the age of individual animals and reveal how quickly they developed. Many early dinosaurs appear to have reached adulthood faster than many older reptiles living at the same time. The brains of the first dinosaurs were not especially large, but they contained well-developed areas responsible for balance, movement, and vision. Large eye sockets suggest that eyesight played an important role in finding food and avoiding predators. Good vision allowed hunters to judge distance accurately while chasing prey. Plant eaters also benefited by spotting danger before predators came too close. The sense of smell may also have been important. Openings inside fossil skulls show the areas where nerves connected to the nose. These structures suggest that many early dinosaurs could detect food, recognize members of their own species, and sense danger through smell. Hearing also helped them remain alert to sounds made by predators, prey, or changing weather. The first dinosaurs reproduced by laying eggs. Although direct fossil evidence from the earliest species is limited, later dinosaur fossils clearly show egg-laying, and scientists believe this method was already established among their earliest ancestors. Females likely searched for safe places where the ground remained warm enough for eggs to develop. They may have buried their eggs under soil, sand, or plant material. Young dinosaurs hatched much smaller than adults and had to survive in a world filled with many dangers. Long before the first dinosaurs became the most successful land animals on Earth, many other powerful hunters already lived across the ancient world. These animals ruled the land during the Triassic Period, a time that began about 252 million years ago after the greatest mass extinction in Earth's history. Life was slowly returning after that terrible event, but the world was still very different from the one that later became famous for giant dinosaurs. The land was joined together as one huge supercontinent called Pangaea. Large deserts covered many areas, while rivers, lakes, forests, and wetlands spread across other regions. The weather was often hot, and many places received little rain for long periods. Even with these difficult conditions, animals continued to grow, spread, and fill the empty places left behind after so many earlier species disappeared. During the early part of the Triassic period, reptiles became some of the most successful land animals. They slowly expanded into many different habitats and developed many body shapes. Some stayed small and fed on insects or plants. Others became larger and hunted other animals for food. As millions of years passed, these hunters became stronger and more skilled. They filled the role of top predators long before the first large dinosaurs appeared. The world of the Triassic was full of dangerous meat-eating reptiles that used different methods to catch prey. Many of these early predators belong to a large group of reptiles known today as archosaurs. This group later produced dinosaurs, crocodiles, flying reptiles, and birds. During the Triassic period, however, dinosaurs were only a small part of this larger family. Other archosaurs were often bigger, stronger, and more successful than the earliest dinosaurs. These animals spread across wide areas of Pangaea and became the main hunters in many environments. One of the best known of these early predators was Prehistoric. This large reptile lived during the later part of the Triassic period in what is now North America. It was among the biggest meat-eating animals of its time. Scientists believe it could grow to around 13 feet in length and weigh several hundred pounds. Its body was built for strength. It had a large head with powerful jaws filled with sharp teeth that could tear flesh from its prey. The skull was deep and strong, allowing the muscles of the jaw to produce a powerful bite. Prehistoric had strong legs that helped it move across different kinds of ground. Some scientists believe it could sometimes walk on its two back legs while moving quickly, although it likely spent much of its time using all four legs for support. Its long tail helped keep its body balanced while moving. Strong claws allowed it to grip the ground and hold struggling prey. Fossils show that this predator had thick bones and powerful muscles, making it one of the most feared hunters in its environment. The places where Prehistoric lived contained rivers, floodplains, forests, and open spaces. Many different animals shared these habitats. Small reptiles searched for insects among plants. Plant-eating reptiles gathered near water, where food was easier to find. Early amphibians remained close to lakes and rivers. Small early dinosaurs also lived in these same areas. Prehistoric probably hunted many kinds of animals, depending on what was available. It likely waited for chances to attack rather than chasing prey over long distances. Another important predator from the Triassic period was Saurosuchus. This giant reptile lived in what is now South America during the late Triassic. It was one of the largest hunters living on land before the rise of large dinosaurs. Its body reached impressive lengths, and its heavy skull contained rows of sharp teeth designed for cutting through meat. Fossils show that Saurosuchus had a long body, strong limbs, and a heavy tail that helped support its movement. Saurosuchus lived in an environment filled with rivers, forests, and open areas where many animals searched for food. Plant-eating reptiles, early dinosaurs, and smaller hunters all shared these lands. As one of the largest predators, Saurosuchus likely hunted many of these animals whenever the opportunity appeared. It probably relied on surprise attacks, using its powerful jaws to capture prey before it could escape. The skull of Saurosuchus had openings that made it lighter while still remaining strong. This allowed large jaw muscles to attach firmly, giving the animal a powerful bite. Sharp teeth were replaced throughout its life whenever older teeth became damaged or worn down. This ability helped it remain an effective hunter for many years. Prehistoric was another important predator from the Triassic world. Fossils of this reptile have been discovered in what is now Brazil. Like many other large archosaurs, Prehistoric had a massive head, strong neck, powerful body, and sharp teeth. Its limbs were placed more directly beneath the body than those of many earlier reptiles, giving it better support while walking. This body design allowed it to move with greater stability across different kinds of ground. Prehistoric probably hunted many different animals that lived in its environment. Small reptiles, young plant eaters, amphibians, and early dinosaurs may all have been possible prey. Scientists believe it may have hunted alone, although there is no clear evidence showing whether these animals sometimes lived or hunted in groups. Most fossil discoveries suggest that individual hunters probably searched for food by themselves. The Triassic landscape contained many dangers for smaller animals. A young reptile searching for insects could suddenly become the target of a larger hunter. Plant eaters grazing near rivers always faced the risk of attack. Even other meat eaters had to remain alert because larger predators could threaten them. Life during this period required constant awareness of danger. Another large predator, known from the Triassic, was Phascolarctos. Fossils of this animal have also been found in South America. Scientists believe it may have been among the largest land predators before giant meat-eating dinosaurs became common. Although only part of its skeleton has been found, the available fossils suggest a very large body with a long skull and strong jaws. Much about Phascolarctos remains uncertain because complete skeletons have not yet been discovered. Even so, the bones that have been recovered show that it was a powerful member of the archosaur family. The rivers and floodplains where Phascolarctos lived supported many forms of life. Ferns, seed ferns, conifers, and other ancient plants covered parts of the landscape. These plants fed large plant-eating reptiles. Smaller hunters followed these plant eaters, and larger predators followed both. This created a living community where every animal depended on the survival of many others. Not every successful predator reached enormous sizes. Some hunters remained medium-sized, but became highly effective through speed, sharp senses, and quick movements. Smaller archosaurs hunted insects, fish, amphibians, and young reptiles. These animals filled important roles within Triassic ecosystems. Their success helped keep populations of smaller animals under control, while also providing food for larger predators. Many Triassic predators had excellent eyesight. Eyes placed toward the front or sides of the skull allowed them to notice movement across the landscape. Good vision helped them detect prey from a distance or notice danger coming from another hunter. A strong sense of smell also played an important part in finding food. Hunters could detect the scent of injured animals or locate carcasses left behind by other predators. Sharp teeth were one of the most important hunting tools. The shape of these teeth varied among different species, but most meat-eating reptiles had pointed teeth designed to grip flesh. Strong jaw muscles allowed these animals to bite deeply into struggling prey. Teeth often broke during hunting, but new teeth usually grew to replace damaged ones. This steady replacement helped predators remain effective throughout their lives. The claws of many Triassic predators were also useful. Strong curved claws helped hold prey, while powerful jaws delivered deadly bites. Claws also provided support while moving over rough ground, climbing riverbanks, or digging shallow resting places. Some predators may have used their claws during fights with members of their own species over territory or mates. The bones of these reptiles reveal that their bodies were well suited for active lives. Strong leg bones supported heavy weight while allowing movement across long distances. Flexible necks allowed quick strikes when prey came within reach. Heavy tails helped maintain balance while walking or turning. Thick bones protected important parts of the body during struggles with prey. The Triassic world was filled with changing seasons. Rivers sometimes overflowed after heavy rains, creating rich floodplains where plants grew well. During dry seasons, many water sources became much smaller. Animals gathered around the remaining rivers and lakes because fresh water was necessary for survival. These places often became dangerous hunting grounds, where predators waited for thirsty animals to approach. Many fossil sites preserve the remains of animals that died near ancient rivers. Floods sometimes buried bodies beneath layers of mud and sand. Over millions of years, these layers hardened into rock, protecting bones from destruction. Today, scientists carefully remove these fossils from the surrounding rock to study the lives of these ancient predators. Every new discovery helps increase our understanding of the animals that ruled the land before dinosaurs became the dominant creatures. The fossil record also shows that these predators lived alongside many unusual reptiles that no longer exist today. Some animals had heavy armor covering their backs, others had long necks, wide bodies, or special teeth for eating tough plants. This wide variety of life created many opportunities for large meat-eating reptiles to find food in different environments. Each predator occupied its own place within the changing ecosystems of the Triassic world, and new fossil discoveries continue to reveal additional details about how these remarkable hunters lived, moved, hunted, and survived across the ancient landscapes of Pangaea. The Triassic period was the first period of the Mesozoic era. It began after the largest mass extinction in Earth's history. At the beginning of this period, the land, the seas, the climate, and the living things on Earth were very different from what had existed before. Many kinds of plants and animals had disappeared during the Great Extinction that ended the Permian period. The world was left with many empty places where living things had once existed. During the Triassic, life slowly spread again into these empty places. New kinds of plants appeared, new groups of animals became more common, and the first dinosaurs, the first true mammals, and many other important creatures began their history. Scientists divide the Triassic into three main parts so they can better understand the long changes that happened during this time. These parts are called the Early Triassic, the Middle Triassic, and the Late Triassic. Each part lasted for many millions of years and had its own conditions, plants, animals, and important events. The Early Triassic began about 252 million years ago. It started immediately after the Great Extinction that ended the Permian period. Earth was still recovering from the terrible losses that had affected almost every form of life. The land looked empty in many places because forests had been destroyed during the extinction. Large areas had only a small number of plants growing on them. Rivers often carried loose soil because there were not enough roots to hold the ground together. Dust, sand, and mud were carried into lakes and seas. Many places had dry conditions, although some regions received seasonal rain. Temperatures were often very warm across much of the world. The continents were joined together as one giant landmass called Pangaea. Since almost all the land was connected, there were very few large barriers that stopped animals from moving from one place to another. Many species were able to spread across great distances. At the same time, the huge size of Pangaea created many dry inland areas because moist air from the oceans could not easily reach the center of the continent. This caused large deserts to develop in many places. The oceans also needed time to recover. Many marine animals had disappeared during the extinction. Coral reefs were almost completely gone. Many kinds of shellfish, fish, and other sea creatures had become very rare. The food chains in the oceans had been badly damaged. Small groups of surviving animals slowly multiplied and spread into empty habitats. This recovery did not happen quickly. It took millions of years before ocean life became rich again. Plants during the early Triassic were not as widespread as they had been before the extinction. Small seed plants, ferns and other simple plants slowly covered open ground. Forests did exist in some wetter places, but they were smaller and less common than before. As plants spread across the land, they slowly improved the soil. Their roots helped hold the ground together and reduced erosion. Leaves and dead plant material added nutrients to the soil, making it easier for more plants to grow. Many animals living on land during the early Triassic were survivors from older groups that had already existed before the extinction. Some of these animals belonged to a group called therapsids. These animals had many different body shapes and sizes. Some ate plants while others hunted smaller animals. A few therapsids later gave rise to the first true mammals, although true mammals had not yet become common during the earliest part of the Triassic. Another important group during this time included reptiles known as archosaurs. These reptiles would later produce crocodiles, dinosaurs, and flying reptiles. In the early Triassic, archosaurs were still becoming established. They lived alongside many older groups that had survived the extinction. Some walked on 4 legs, while others could move on 2 legs for short periods. Their bodies slowly developed features that allowed them to become more successful in later ages. Amphibians were also important members of early Triassic ecosystems. Many of them were large animals that spent much of their lives near rivers, lakes, and swamps. Their moist skin meant they needed water for breeding. They hunted fish, insects, and other small animals. In places where permanent water remained throughout the year, these amphibians were often among the largest animals. Insects survived the Great Extinction better than many larger animals. Beetles, dragonflies, and many other kinds of insects continued to live in forests, grass-like plant communities, and near freshwater. They became food for reptiles, amphibians, and other insect-eating animals. As plant life recovered, insect populations also increased because they had more food and more places to live. Life during the early Triassic was often difficult because the environment remained unstable. Long dry seasons affected many regions. Sudden floods sometimes followed heavy rains. Wildfires may have occurred in dry forests. Some lakes dried up during hot seasons before filling again when rain returned. Animals had to adapt to these changing conditions if they were to survive. As millions of years passed, Earth slowly became more stable. Plant life became thicker in many regions. Rivers developed more permanent channels. Forests spread into areas where conditions became suitable. Animal populations increased. More species appeared through evolution. These gradual improvements marked the transition toward the Middle Triassic. The Middle Triassic began about 247 million years ago. By this time, the recovery from the Great Extinction had made significant progress. Ecosystems became richer and more complex. Many groups of plants and animals that had struggled during the early Triassic now expanded into many different environments. Food chains became longer and more balanced. There were more predators, more plant-eaters, and more small animals filling different roles in nature. Forests became larger in many regions during the Middle Triassic. Conifers became important trees across wide areas. Seed ferns, cycads, ginkgo relatives, and many other plants also spread. Thick vegetation created homes for insects, reptiles, amphibians, and many smaller animals. Fallen leaves built deeper soils, allowing forests to continue expanding. Climate during the Middle Triassic remained warm over much of Earth. Many inland areas were still dry, but seasonal rainfall supported forests in suitable regions. Rivers, lakes, and wetlands became more common in places where water was available throughout the year. Coastal environments also supported many different forms of life. the seas experienced a major recovery during the Middle Triassic. Coral reefs slowly returned in some places. Shellfish became more diverse. Many fish species appeared in larger numbers. Marine reptiles became important predators in the oceans. Some had long necks, some had large heads with powerful jaws, and others were fast swimmers that chased schools of fish. Ichthyosaurs became some of the most successful marine reptiles during this time. They spent their entire lives in the sea. Their bodies allowed them to swim efficiently through open water. They hunted fish and squid-like animals. Fossils show that some gave birth to live young instead of laying eggs on land. Nothosaurs lived mainly in shallow coastal waters. They had long bodies, webbed feet, and sharp teeth for catching fish. They often stayed close to shore where food was plentiful. Other marine reptiles occupied different parts of the ocean, showing that sea life had become much more varied than during the early Triassic. On land, archosaurs continued becoming more successful. Many different kinds appeared. Some hunted other animals, while others ate plants. Their legs gradually became positioned more directly beneath their bodies, making movement more efficient. This body design later became important for dinosaurs and crocodile relatives. The first true dinosaurs appeared near the end of the Middle Triassic. They were small animals compared with the giant dinosaurs that would live much later. Many were light in weight and moved quickly. Some walked on 2 legs. Others may have used 4 legs during certain activities. They hunted insects, small reptiles, and other small animals, while a few early species fed mainly on plants. These first dinosaurs were still only a small part of the animal world. They did not yet dominate the land. Many other reptiles were more common and often much larger. Dinosaurs lived beside these older groups and slowly spread into different environments. The ancestors of crocodiles also continued developing during the Middle Triassic. Some lived near rivers and lakes, others hunted on land. Their body shapes were much more varied than those of modern crocodiles. Over time, different branches of this group adapted to different habitats. Therapsids still remained important in several regions. Some large plant-eating species grazed on low-growing vegetation. Smaller meat-eating forms hunted insects and small reptiles. Within this group, tiny mammal relatives continued evolving. Their bodies became better suited for active movement, improved hearing, and more efficient chewing. The first true mammals probably appeared during the later part of the Middle Triassic. These mammals were very small, often no larger than modern mice. They were likely active at night, feeding on insects and other tiny animals. Their small size allowed them to hide from larger predators. Although they remained rare, they represented the beginning of a group that would later spread across every continent. Insects became even more diverse during the Middle Triassic. Different kinds of beetles, flies, early relatives of butterflies and moths, dragonflies, and many other insects filled forests and wetlands. They pollinated some plants, broke down dead material, and served as food for many larger animals. The Middle Triassic was also a time when ecosystems became increasingly connected. Forests supported insects. Insects fed reptiles, amphibians, and mammals. Plant eaters depended on expanding vegetation. Predators relied on healthy populations of prey. Rivers carried nutrients that supported freshwater life, while coastal waters connected land ecosystems with the oceans. The end Triassic mass extinction was one of the most important events in the long history of life on Earth. It happened at the very end of the Triassic Period, after millions of years during which plants, animals, and other living things had slowly recovered from the earlier Permian mass extinction. By the time the Triassic was coming to an end, the world had become home to many different kinds of life. Forests covered large areas of land, where enough rain fell. Dry regions supported plants that could survive with little water. Rivers, lakes and wetlands provided homes for fish, amphibians, reptiles, insects, and many other living things. The seas were filled with shellfish, corals, ammonites, marine reptiles, and countless tiny organisms that floated in the water. On land, dinosaurs were only one group among many reptiles. They had not yet become the most successful animals on Earth. Many other reptiles lived beside them and often filled the most important roles in their environments. Life during the late Triassic was rich and varied. Different kinds of reptiles lived in forests, open plains, river valleys, and deserts. Some were large hunters, while others fed on plants, insects, fish, or small animals. Early crocodile relatives lived in many different forms. Some walked mainly on land with long legs. Others spent much of their time in rivers and lakes. Large amphibians still survived in wet places, although they were not as common as they had been in earlier times. Small mammals and their close relatives hid among plants, dug burrows, and searched for food, mostly during the night. Insects filled the air and covered the ground. They pollinated plants, fed on leaves, hunted other insects, and became food for many animals. The oceans were also full of life. Coral reefs supported many different creatures. Fish of many shapes and sizes swam through shallow and deep waters. Marine reptiles hunted fish and squid-like animals. Ammonites drifted through the seas in huge numbers. Shellfish lived on the sea floor. Tiny floating organisms formed the base of many food chains. Every part of the sea supported different kinds of life that depended on one another for food and survival. The land itself looked very different from the modern world. Most of Earth's land was still joined together as the giant supercontinent called Pangaea. This huge landmass stretched across many climate zones. Some regions received regular rainfall, while others were extremely dry. Large deserts covered many inland areas because they were far from the oceans. Coastal regions often received more moisture. Rivers carried water across the land, creating places where plants and animals gathered in large numbers. The climate during the late Triassic was often warm. Many places experienced long dry seasons, followed by periods of heavy rain. Temperatures could remain high for much of the year. Living things had slowly adapted to these changing conditions over millions of years. Plants developed ways to reduce water loss. Animals found different methods of surviving during dry seasons. Some migrated to wetter areas. Others remained close to rivers or lakes. Some dug underground shelters where temperatures stayed more stable. Although life appeared stable in many places, powerful natural forces were already changing the planet. Deep below Earth's surface, huge movements were taking place. The crust of the planet was slowly being pulled apart. Pangaea was beginning to break into separate landmasses. This process happened very slowly over millions of years, but it placed enormous pressure on the rocks beneath the surface. Eventually, that pressure led to one of the greatest periods of volcanic activity in Earth's history. Scientists believe that massive volcanic eruptions began near the end of the Triassic Period. These eruptions were not small events that lasted only a few days or weeks. Instead, they continued again and again over a very long time. Thick streams of lava poured across the land. Huge cracks opened in the ground, allowing molten rock from deep inside Earth to reach the surface. Large areas became covered by layer after layer of hardened lava. The volcanic region where these eruptions happened is now known as the Central Atlantic Magmatic Province. Today, pieces of these ancient lava flows can be found in parts of North America, South America, Europe, and Africa. These rocks show that all of these regions were once connected before the Atlantic Ocean formed between them. The volcanic activity spread across an enormous area, making it one of the largest volcanic events ever known. Every major volcanic eruption released large amounts of gases into the atmosphere. Among these gases was carbon dioxide, which is known for trapping heat. Volcanoes also released sulfur dioxide and other chemicals. Ash and dust entered the sky as well. The amount of material released was far greater than anything seen during ordinary volcanic activity. These gases slowly changed the atmosphere and affected the climate across the entire planet. At first, sulfur gases and volcanic ash may have blocked some sunlight from reaching Earth's surface. This could have caused cooler conditions for a short time in some places. Plants depend on sunlight to make food, so any reduction in sunlight would have affected their growth. Cooler temperatures would also have changed weather patterns. Some areas may have received less rain, while others experienced different seasonal conditions than before. As time passed, the growing amount of carbon dioxide in the atmosphere caused Earth to become warmer. Higher temperatures affected land and sea alike. Regions that were already hot became even hotter. Rainfall patterns changed. Some rivers dried up more often. Lakes shrank. Wetlands disappeared in many places. Forests experienced increasing stress as changing weather made it harder for many plants to survive. Plants form the foundation of life on land. When large numbers of plants began to die, many animals lost their food supply. Plant-eating animals struggled to find enough leaves, seeds, stems, and other plant material. As these animals became fewer, hunters also faced food shortages. The effects spread through entire ecosystems. Even animals that survived the changing climate often found it difficult to reproduce because food had become less available. The oceans also experienced serious changes. Carbon dioxide dissolved into seawater, making the water more acidic. Many sea creatures built their shells or skeletons from minerals that became harder to use in more acidic water. Corals, shellfish, and many tiny marine organisms found it difficult to grow strong shells. Some populations became much smaller. Others disappeared completely from certain areas. Warmer ocean temperatures created additional problems. Warm water holds less oxygen than cooler water. At the same time, changing ocean circulation prevented fresh oxygen from reaching deeper parts of the sea. Many marine animals depended on oxygen-rich water for survival. As oxygen levels dropped, large parts of the oceans became difficult places for many forms of life. Animals that could not tolerate these conditions died in large numbers. Scientists study ancient rocks to understand what happened during this time. Layers of rock contain chemical evidence that records changes in Earth's environment. Certain forms of carbon preserved in rocks show that enormous amounts of carbon entered the atmosphere. Other chemical signals reveal changes in ocean temperatures and oxygen levels. Fossils found above and below the extinction layer show which groups survived and which disappeared. The fossil record reveals that many different kinds of living things vanished during this event. Numerous marine species disappeared forever. Many ammonites became extinct, although a few survived and later spread again during the Jurassic Period. Coral reefs suffered heavy losses. Many shell-forming animals became rare or disappeared entirely. Tiny floating organisms that supported marine food chains also experienced major declines. Life on land suffered as well. Many large amphibians disappeared. Several important reptile groups that had been successful throughout much of the Triassic vanished before the Jurassic began. Numerous plant species became rare in many regions. Forests changed as different kinds of plants replaced those that could no longer survive the new conditions. Insects were also affected, although many groups managed to survive and continue evolving. Some of the reptiles that disappeared had dominated their environments for millions of years. Their extinction left empty places in many ecosystems. Animals that had depended on them, either as food or as part of the balance of nature, also faced new challenges. Food chains changed as surviving species adapted to the loss of familiar plants and animals.